Hello friends, so let's talk about the one sample t-test. In this video, we will talk about the basic concepts of one sample t-test, and we will conduct a one sample t-test. Next, we will graph the data to get a sense of the mean and variability of the data. And in the last, we will talk about the assumptions of one sample t-test. So let's get started. For example, Gazprom company fills propane tanks uh, because propane liquid expands when heated, so the tanks must be filled to only 80% capacity to allow room for possible liquid expansion on a hot day. When the tank is 80% full, it holds 10 kilograms of propane. On average, is Gazprom able to fill tanks to hypothesize a weight of 10 kilograms? We can use one sample t-test to determine whether the average weight of filled propane tanks is equal to the 10 kilogram target. In general, one sample t-test is used to determine whether the population mean is equal to a hypothesized value. To use this test, we need the data that are both numeric and random. We'll perform the test in 4 steps. First, we'll establish a hypothesis about the mean. Next, we collect a random sample of data from the population and measure them. And then uh, we'll graph the data. And finally, we'll conduct and interpret the results of the one sample t-test. For a one sample t-test, your null hypothesis states that the population mean equals the hypothesized mean. The alternative hypothesis states that they are not equal. So what are the null and alternative hypotheses for the weight of Gazprom propane tanks? Okay, so the HO is mean weight equal 10 kg, and the H1 is mean weight not equal 10 kg. Next, we collect random data from the population. We collect things randomly to help ensure that the sample is representative of the entire population of propane tanks, and then measure their weight in kilograms. Okay, so let's recap. We use one sample t-test to determine whether a population mean is equal to a hypothesized value. So far, we've determined the null and alternative hypotheses and collected a random sample from the population. In the next lessons, we'll use an individual value plot to display the data and then use a statistical test to make a decision about the null hypothesis. Okay, so in the last lesson, we learned that the Gazprom can use a one sample t-test to evaluate whether propane tanks are being filled properly. We've established our null and alternative hypothesis and weight the sample of filled propane tanks before we conduct the hypothesis test. So let's graph our data to get a sense of the mean and variability of tank weight. First, let's look at an individual value plot of the weight data. So what does this graph tell you about the mean and the variability of the sample data? Okay, so notice that the range of tank weight values, they range from less than 9.5 kg to greater than 10.4 kg. The individual value plot reveals that the data are highly variable, although many of the sample weights appear to be below hypothesized value of 10 kg. So we need to analyze the results of the one sample t-test to draw conclusions about whether the mean weight of the population of propane tanks is equal to 10 kg. The individual value plot gives us a sense of the mean and variability of our data. Next, we'll look at the t-test statistics and decide whether to reject or fail to reject the null hypothesis. So let's return to GasPro, where we want to test the null hypothesis that the mean weight of propane tanks is 10 kg. We collected our data and graphed this on an individual value plot. Now we are ready to perform one sympathy test. So what will the results tell us about the mean weight of the tanks? Let's interpret the results. To decide whether to reject or fail to reject the null hypothesis, we focus on the test statistic and p-value. Here is the observed value of the t-test statistic, which is used to compute the p-value. Recall that the p-value is probability of obtaining a test statistic that is at least as extreme as the calculated value if the null hypothesis is true. In other words, if the population mean is really 10 kg, then the probability of randomly selecting 100 tanks from the population and obtaining this test statistic is 0.46. Suppose we set alpha for our test is 0.05. So should we reject or fail to reject the null hypothesis? The t-test results indicate that the sample mean is 9.9854. The test answers the question if V is equal to 10. So how likely is it to see a sample mean this different from 10 kilograms? The answer is given as the p-value, which for this test is equal to 0.46. Because the p-value is greater than alpha, so we fail to reject the null hypothesis. There is insufficient statistical evidence to claim the population mean is not equal to 10 kg. The sample mean 9.9854 is an estimate of the population mean. So let's now look at the confidence interval. The range of likely values for the population mean based on both the sample mean and the sample variation. We can be 95% confident that the true mean of the population is between 9.9463 and 10.0245 because 10 is within the confidence interval. It is likely that our sample came from a population with a mean that is equal to the target. Okay, so let's review. The one sample t-test procedure provides both a confidence interval and p-value. We use the p-value to determine whether a population mean is equal to a hypothesized value. We use the confidence interval to obtain a range of reasonable values for the population mean. Remember, we should always consider the practical implications of our guidance so we can best apply the results to our processes. Okay, so when performing hypothesis tests, we always make assumptions about the sample data. For the one sample t-test, we assume we have a random sample of numeric data from a normally distributed population. To illustrate, recall the one sample t-test we performed. We failed to reject the null hypothesis that the mean weight of propane tanks is equal to 10 kg. If the weight data do not meet these assumptions, the results of the analysis can be misleading. When when might our data violate this assumption? Our data might fail to be random if we don't use good sampling practices. For example, if an operator cannot lift more than 10 kilograms, then our sample will be biased towards things lighter than 10 kilograms. The result will be a sample that is not representative of the entire population of propane tanks. Biased data do not reflect the entire population, and so conclusions based on these data may be misleading. So what about the second assumption? Many data come from non-normal distribution. Fortunately, the one-sample t-test is very robust to violations of the normality assumption, provided that the data are random and numeric. But if the data are highly non-normal, we may need to use another method for analyzing the data. For example, a data transformation or non-parametric procedures may be appropriate. So we will talk about these techniques later. Okay, so let's return to the gas pro example. So do the thing with data meet the one sample t-test assumptions? In previous lesson, we randomly sampled things and determined their weight and a numeric variable. We can also look at a histogram, which verifies that the thing with data are from a normally distributed population. So the data meets the one sample t-test assumption. So we can be confident in our results. Thank you for listening. In the next lesson, we will talk about the two variances test.